This is all about iron salt aerosol, safe, scalable, inexpensive, negative emission technology. And this is, my name is Clive Elsworth, and it's the brainchild of Franz Ost. So Franz, I will be calling upon mostly, well, I mean, he might interject with answers and answer questions quite a lot at the end. So every climate scientist I come across is concerned about the situation, especially at the moment. We don't know if we've already entered a tipping point with interacting, amplifying feedbacks could be underway. Looks as though they are, especially in the Arctic. We've had these very high temperatures, melting permafrost. We're worried about methane release, and it doesn't bear thinking about what could happen. So there seems to be a need for negative emissions. So now people say, oh no, but the policy should be to reduce greenhouse gas emissions. Well, yes, but that's now inadequate as the only policy. That's our stance, certainly mine. Greenhouse gas removal is now essential if we want to avoid these short-term risks. And all these very long lists of things. I've just listed a few things here. Uninhabitable hot regions, and people dying of heat stroke. And really, the thing that I wouldn't say keeps me up at night, but it just seems incorrect. It's wrong to allow settlements that have been there for thousands of years, what were fishing villages and are now big metropolises, to just be overwhelmed by sea level rise. There are people who say that it's too late for even that now, but I think there's something that can make a big difference in that respect. Then we should be talking about it. We should be funding it and learning as much as we can about it. So this is iron salt aerosol. Here's a list, it's not a full list of its cooling effects. The Australians actually have a website. It's been there for at least a year, ironsaltaerosol.com, and it lists 12 cooling effects. So these are the main ones. Depletes greenhouse gases, as you can see there, methane. And I'm going to say a little bit more about these and how these work in a moment. So this is just the overview. Methane by oxidation. It's like combustion, but oxidation is really the correct term to use. CO2 by absorption into the ocean. Controversial. We have a lot to say about that. I'm planning actually initially for this to actually skip most of those slides on the ocean. If there are questions about the ocean, I may go back to those as appropriate. Okay. Tropospheric ozone is also contributing to warming, and iron salt aerosol triggers its sudden destruction on a large scale. So also it makes black-brown carbon particles more hydrophilic, so they were more washable out by rain, and that's another significant warming agent. Then the other thing it does, the other cooling effect, is albedo increases the Earth's reflectivity where it's in operation. So acting as these CCNs, cloud condensation nuclei, so like seeding clouds, makes them whiter, makes them last longer. And if iron salt aerosol is operating in the ocean, then phytoplankton also, they produce what people know as the smell of the sea, which is another aerosol emission from phytoplankton, so a little bit acidic, and it makes more cloud condensation nuclei, get marine clouds, and they also make, if there's enough of them, a difference to the color of the ocean, so it brightens the ocean a little bit. I first learned that from Pearce, actually, from your video talking about the oceans used to be turquoise, and now they're rather dark blue. Okay, so what is iron salt aerosol, which we abbreviate to ISA? So an aerosol, it's like little invisible tiny particles. That's what an aerosol is. They carry around in the air. It's like a smell is an example of an aerosol. I think we know you spray it under your arm. As another example. It occurs naturally above the ocean, and it's already removing greenhouse gases. And the ones I've just listed must be, and we haven't been able to measure it yet, but there's been some lab tests done. Formed over several days. This stuff is a naturally occurring substance, forms over several days. Iron in dust or smoke particles. I've got a diagram in a moment that's going to show all this. So basically, it's the iron from particles that blow over the ocean, the salt in sea spray, and natural acidic aerosols. They all combine to make iron salt aerosol. And it usually rains out within about 3 weeks. So what is it exactly? It's ferric chloride, not ferrous chloride, but ferric chloride. So that's iron 3 chloride, FeCl3, Fe being symbol for iron. Okay, droplets. So aqueous droplets, or if you had, depending on the humidity, if it's very dry air, then basically just get solid particles. The water evaporates away. Here's a little bit of chemistry. So I'll just give an overview of this. It looks quite complicated. So let's start down here. We have some acid, H2SO4 is sulfuric acid, quite naturally occurring, coming from the phytoplankton. The idea is the ocean's under here. I've cut off that bit of the picture. Reacting with airborne sea salts, sodium chloride, giving off hydrogen chloride gas. That's hydrochloric acid. This all occurs. I was quite shocked actually when I learned that this is all going on above the sea quite naturally. Obviously, not in concentrations which are harmful to human beings or any other animals, but they're there nonetheless. Reacting with this is iron, kind of oxyhydroxide. This is basically rust, a little bit of tiny speck of rust in a dust particle. Reacting with hydrogen chloride to produce iron 3 chloride. The next thing that happens is we have a photon coming in from the sun. So in presence of sunshine, iron 3 chloride is light sensitive. It becomes iron. It goes from being iron 3 chloride to iron 2 chloride. So iron has these different oxidation states. It changes to iron 2, and then loses as a result a chlorine atom. Not a chlorine ion, but a chlorine atom. Chlorine normally goes around as molecules of Cl2. So it's a bit unusual to get a chlorine atom like this. And atmospheric chemists know very well that this is, well, they'd call it a chlorine radical. They know that it's very reactive. It's a strong oxidant. And this, it turns out, oxidizes, here's a methane molecule, oxidizes methane in the air about 16 times faster than OH. This is an OH radical. So this is a little circle in front. It means it's a radical. So not a charged ion. Okay, and in humid air, it turns out that, well, methane does not is not very soluble in water, so it doesn't get absorbed into droplets of water. OH radicals do rather get absorbed by several orders of magnitude. Chlorine's at about halfway in between. So basically, when you have very humid air, the speed of oxidation by OH radicals, which is the normal mechanism by which methane, that's why it has quite a short half-life, oxidizes methane, it goes right down. Whereas, this chlorine carries on. So it'd be quite a good idea, I'm making the case, for iron salt aerosol. It keeps going, oxidizing methane. And once methane is oxidized, you just get CO2 and water. Water hasn't been put on here because maybe it's a bit too obvious. But it produces CO2. And the other thing that's happening here is we see a bromine radical. It tends to be bromine that breaks down or triggers the destruction of a large amount of ozone, O3 being ozone, just becoming O2. Okay, and then also becoming cloud condensation nuclei and even sea salt. So that's the chemistry in the atmosphere. When a particle settles into the ocean, something very different happens. If it's iron poor, if it's an iron poor region of the ocean, then phytoplankton needs iron, so that makes a big difference. You get quite a large increase depending on the species of phytoplankton. You can get you don't need much iron to cause quite a large increase in primary productivity. Basically, CO2 drawdown and converted into organic carbon from an iron particle settling in the ocean. A little bit more on that, and we've got at least one slide on that in a moment. So that was all what occurs naturally. Here we are So thinking about, well, okay, if that works so well and it's a natural process, could we boost that? Could we do a little bit more of that artificially? The answer is, well, we're saying yes. Yes. So very simply, more iron salt aerosol in the atmosphere would remove greenhouse gases faster. Methane, now this is, it's difficult to say. We all operate from our personal resources. We think really from a properly, this kind of scaled up operation that we can think of. You know, methane could be getting depleted from the atmosphere 4 times faster. That's very much an estimate. We want to do research to be able to understand that better and be able to predict that better. Then CO2, possibly, we like to think. We can't see right now. Franz and I, well, it's really Franz's work, cannot see harmful effects from, and this is a big number. Oceanographers look at that and say, what? You know, that's a big number. This is the rate of human emissions. A slide on that in a moment. Okay, big numbers here. It's not expensive. This is really a very conservative estimate to include, well, first of all, one of the most expensive ways of putting iron 3 chloride aerosol, you know, to putting it into the air, and also including a lot of money for research work. So again, it's a very rough estimate. Iron 3 chloride is a substance, is, you know, chemicals already widely used. It's used in water treatment. If you go on Wikipedia, you'll see a very long list of things. It was also used in the very first photographic film due to its light sensitivity, I'm told. So,
Clive,
yeah.
here. Do you have an estimate of price per ton of methane?
Can we deal with that at the end, Peter? Let's have all the questions at the end, if that's okay.
Most certainly.
Okay. And I don't have an answer off the top of my head right now. So let's see if someone else has an answer. So I'm going to whiz through these slides as quick as I can so we can get to questions. So next, nebulization. What do we have in mind? As you can see, away from where people live, the plume needs to be, we call it a plume. Got to call it something. Wouldn't be visible. It needs to be lifted up above sea level so that it can disperse over a long distance, spread out into the air, and be effective over a wide area. Low concentration. The smell of chlorine would already be 1,000 times more than this concentration. We're talking very low concentration by the time it's spread out. Very small particles, less than a micron, and emission should stop when it rains. We don't want to have a high concentration of iron 3 chloride settling into the ocean and causing a phytoplankton bloom. Now, to prevent further warming amplification, we're worried about a spike or a sudden change in the climate. We should be thinking mostly about the methane. We talk about this amongst ourselves every 2 weeks, and we keep saying to each other, make it about the methane. This is the has the highest warming potential, and it's the easiest to remove. So that should be the first response. Have something ready to remove large amounts of methane from the atmosphere to reduce the risk of sudden spike. Okay, so it has a high radiative forcing. We estimate roughly about 1/3 of global warming potential. So 1/3 of global warming forcing is coming from methane. Now, we say that in practice, a realistic way to understand the global warming potential from methane is to say that it's 120 times that of CO2. Now, I expect everyone here has seen, no, it's 33 times or something, different numbers you see. But these metrics, or these estimates, these guidelines are based on this arbitrary figure of whether it's 20 years or 100 years on the half-life, today's half-life of methane over a period of time. But methane is rising, the concentration is rising. So every methane molecule that disappears is replaced by more than one other one. So it makes more sense really to say that each existing methane molecule is exerting this amount of global warming potential. So it's a large contribution to global warming. It's quick and easy to remove with iron salt aerosol. As I've just been saying, it oxidizes, and an iron salt aerosol program would shorten methane's half-life, essentially globally. That would be the aim, because methane moves around the atmosphere, it mixes around the atmosphere. CO2 is much more persistent in the atmosphere, certainly historically. So I just propose to show this one slide on CO2, unless we have questions. Okay, so this is very diffuse ocean iron fertilization. There has been addition of sulfate or some kind of slurry, liquid from a ship into the ocean, and researchers have seen very large, in some cases, phytoplankton blooms. But using an aerosol, it's very, very diffuse, as these later points make. So to absorb, if we're going to absorb 40 gigatons of CO2, we have to be careful whether we mean carbon or CO2. So this is 40 gigatons of CO2 per year. We would aim to, this is as a first approach, increase primary productivity by this much, 2 grams of carbon per meter squared per day in the ocean. If this happens over, the North Atlantic is not iron poor. There's plenty, well, I wouldn't say plenty of iron, but there's certainly a much higher measurable amount of iron in the ocean. Wouldn't make much difference. Go to the Pacific, huge areas of the Pacific are like deserts, very low iron concentration. This is our proposal. Needs a settling rate of, now this is a 20th of a milligram per meter squared per day. This is again estimated. Some oceanographers will say you're not going to get much for that. So we prefer to start small. If you want to try and imagine that, a kilogram per 20 kilometers squared per day is what that's equivalent to. And given that everybody has to talk in terms of football fields, 20 kilometers squared is that many football fields. So we're talking about roughly about 1/3 of a gram of iron per football field per day over this very large 16.4 million square kilometers. That's about 4% of the ocean, and this much iron per year. 280,000 tons of iron, plus of course the chloride. Each emission facility would produce, so this is try and imagine what would this look like. 5 tons per hour of iron-free chloride, serve an area 1,000 kilometers like this. Means you've got to have only 25 of these facilities. I don't know if it would probably be a little bit more than that, but that order of magnitude I think is rather interesting. It doesn't have to be perhaps such a huge, multi-trillion-dollar operation. It's more like hopefully just billions at most. All right, so no more of this. We've whizzed down through to the rest of it, and we have. So then people say, no. This is just. Sorry, but we're not interested. This is just too good to be true. It's got too many benefits, so you must be fraudulent, because we haven't heard of it elsewhere. So we just don't know what to say about that. You're not telling us what the harmful side effects are. Well, we can't see any. We have looked at the stratospheric ozone layer. We don't want to find that gets affected, but we think it would be protected because these methyl halides are a natural substance from phytoplankton, and they do tend to find their way into stratospheric ozone layer and deplete it somewhat. So there's a natural depletion going on, which would be curbed. These things need to be researched, and for that obviously needs funding. This is the whole point of this presentation. So there need to be strict guidelines for an iron salt aerosol application, both for trials and production. This all has to be kind of signed and sealed. Just simple things, as I said, some of the things would be quite simple, like not emitting the aerosol when it rains or when rain is forecast. Next, we have, we say, okay, so another benefit, boosted fisheries, and people might, I'm just trying to imagine harmful effects. People could say, well, the community composition of your fish is, if the sea life is going to change, if you're going to boost fisheries, some will benefit and some might not benefit so much, or be pushed out of their normal habitat. I just say, you can see here, some perspective needed. There is such plundering of the oceans going on with collapsing fisheries. There's scope, if you have more of something, to manage it well and protect species. Okay, then there's the moral hazard. But greenhouse gas removal will take the pressure off governments to reduce emissions. So, you can't do this because they need to be kept under pressure. But the political reality, they don't really respond anyway. It's economic pressures that overwhelm, dominate climate concerns in most parts of the world. By the same token, should we keep all plastic pollution in the sea? To curb further plastic pollution? I don't think so. It tends to be technical progress that offers solutions. More about this, the biggest moral hazard is doing nothing. So Kevin and I were talking about this earlier today. He was saying that that's the biggest, just doing nothing, that's the biggest hazard. And endless debate with not taking action. It's as if we're on the Titanic steaming towards our iceberg and we're not prepared. Research, we suggest, into this is needed at the very least. And just saying no, we should just reduce emissions, it's tantamount to giving up. The situation in Siberia, which Kevin is much more familiar with than I am, is now beyond most climate models. The IPCC tells me, are saying that the polar amplification can't be predicted or modeled. These amplifying feedback processes, they can't model them because there's too many unknowns. So therefore, better to act now. Well, in a situation that was, mostly reasonably well understood. If we wait for the system to get into, an amplifying feedback mechanism, then our models are going to be less useful to us. But isn't geoengineering a bad idea? Yes, concerns do exist over some other climate repair proposals. So there have been calls that don't have any geoengineering. We try not to call this geoengineering, so we call it climate repair. But the planet is already being hugely geoengineered, changing the atmosphere by increasing its greenhouse gas by 1/3. Effects needs to be reversed. It's so simple. Well, kind of, at least on the top level. By the same token, some drugs are bad, so should all drugs be bad? So should all drugs be banned? Ban tea and coffee and antibiotics. So climate repair proposals are not all created equal. Few people have heard of Salt Aerosol, which is why they're able to say, ban all geoengineering. Once they've heard of Salt Aerosol, I think people will say, no, well, okay, let's think again about that. So why Salt Aerosol? It tackles both short-term and long-term problems. We see it as fully sustainable, it's nature-based, it looks harmless. We'd like to know for sure, we'd like to more research to be done. It's not high-tech and it's inexpensive, especially over the long term after the research effort tails off. So our immediate plans, we're in discussion with the University of Copenhagen, one of the professors there, initially to determine parameters, to do some atmospheric modeling, to find out the kind of thing that's needed, the kind of oxidation amount that's needed to deplete methane, and then do some smog chamber tests to see what effect we get from different droplet sizes, then go to field trials. Of course, this takes time to get permission, do impact assessments, and then scale incrementally with lots of measurements before and after. This is things we talk about every 2 weeks, what measurements we want to take, and so on. We would want this to be properly governed by a governance mechanism, that's fully public. And we're in the process of incorporating. We've got a new website, restoreourclimate.earth, on the way, and that's what the American, it'll be an American nonprofit called Restore Our Climate. And we're engaging in fundraising, basically. We'd like to know that, so this gives us a mechanism to receive funds in a way that's fully above board, with a board of trustees and bylaws, so that any donors can be reasonably confident that the money is going to be spent properly. That's it. Thank you, everybody. It's just about 30 minutes. So, let's have Peter's question first. I see we've got some raised hands. Can you ask your question again, Peter, please?
Yeah, so I was just asking what estimates you have for the cost per ton or cost per something for methane removal.
The cost per ton of methane removal, right.
Or there may be a better way of measuring it, I'm not sure.
I understand the question. I don't have an answer for that.
Can I say something to that?
Please. Yes, please, Franz.
The methane concentration is about 1/1000th of the CO2 concentration. And we calculated similar numbers we need for methane depletion than for CO2 depletion. So 1 ton of methane to remove should be similar to the number of should about 1,000 times that of CO2 removal. Yes,
1,000 times the
1 ton of CO2 removal. 1,000 times of that would be
okay, so we're saying $1 per ton to remove CO2 costs $1 per ton. So is that then $1,000 per ton of methane?
Yeah. You know, we have only 2 ppm methane in the air.
Yeah.
So, it's also fair to say, Peter, it's one of the things that we want to look at with modelling. It's one of the first objectives.
Yes. That's only an extreme rough estimation from me.
There's a number of variables which it's potentially very sensitive to. So, for example, the height that we release the iron salt aerosol could influence quite significantly how effective we are at getting rid of methane. The reason for that is that as we go up in elevation, then HCl starts increasing as we go up in elevation, which then improves the effectiveness of the ISA. Also, as you go up in elevation, you get more UV. So it could well be that if we inject at, say, 100 meters or inject at 1,000 meters, we get 2 completely different performances. So these are all the kind of variables that it's really important for us to try and start getting a handle on as early as possible. The other thing as well, it's not just about getting methane out the atmosphere. It's also about where you get the methane out the atmosphere. So potentially getting methane out the atmosphere in the middle of winter in the Arctic has much more effect than getting methane out the atmosphere in the middle of the summer in the Arctic. But obviously we have no UV in the middle of the winter in the Arctic. So, as I say, depending on where we get the methane out the atmosphere impacts on the change of radiative forcing that we are able to deliver. And again, that's one of the things that we want to try and use modeling to start optimizing just how we design our response to most effectively reducing the radiative forcing first. So there's a lot of variables at the moment.
Good question. So, actually, 2 questions. First, Franz, you said it's 1,000 to 1. The methane is 1/200th the density of CO2. I was wondering where your 1,000 came from. Right, it's 400.
Only from the concentration in the atmosphere.
Right.
You see,
good.
you have
So
about 415 or 418 ppm CO2, and about 1,500 or 1,800
Parts per billion.
parts per billion
Yeah. Okay.
Peter's estimate is slightly closer
methane.
than 1,000. Yeah.
Yeah. So
And
200. Okay. And then Kevin, the other question, if I can remember, it was. You said that it matters where and when. And I would argue that it doesn't, because the atmospheric mixes within a year or so.
Correct.
And
yeah.
the half-life of the methane is 8 years, so hopefully we'll reduce it to 4 years. And so the methane will be mixed, so it doesn't matter where you do it.
To a degree, it will be mixed, but methane distribution in the atmosphere is not entirely homogeneous. It's quite heterogeneous at the moment. We've got significantly more methane in the Arctic region than we have in lower latitudes, and we've got significantly more methane at various altitudes up the way. So we haven't quite got that nice homogeneous distribution of methane in the atmosphere. What we've also got as well, Peter, is the emissions into the atmosphere are also not homogeneous. So we've now got large methane releases coming from the permafrost, from the land-based permafrost, and also now from the thawing and collapse of the subsea structures. And so when you look at the greenhouse gas monitoring network up in the Arctic, there are just frightening spikes coming in the Arctic measurements at the moment. So it may well be that if we tackle the Arctic in the middle of the summer, we can get rid of an awful lot more methane per input of ISA and per unit of time than we can maybe in the lower latitudes. But again, it's stuff that we're going to have to try and evaluate in the testing. And your point's right. You know, that's looking at the distribution and how and the mixing rate is one of the things that we really want to get to grips with understanding there as well.
Yeah, when I've looked at the NASA data, the variation, you know, they have these color maps, and the variation is less than 10% from the densest to the least.
Yeah, and 10% could be quite significant depending on where that variance in 10% is. So if the methane is 10% higher in the Arctic, then the warming impact, the global warming impact, can be a lot greater because we get heat flowing from the middle of the planet to the Arctic regions. So if you then have a slight increase in the insulation of the atmosphere in the Arctic regions, you are stopping a huge amount of heat being released into the atmosphere. Yeah. So potentially, you know, if you could take the Arctic methane level, say, down by, say, 20% in a relatively small region, that might potentially give us an enormous heat release into space that's not happening at the moment. So it depends on, you know, a number of sensitivities. But my hunch at the moment, is that it's not even a hunch. You know, we have higher methane in the Arctic, and my hunch is that the methane in the Arctic is creating much more warming per unit of methane than we get in the lower latitudes, just because of that heat flow dynamic.
Yeah, got it. Okay, thank you.
Sure, thank you, Peter. David Koween, please.
Yeah, thanks. You know, I saw your estimates for the oceanic carbon uptake from diffuse iron fertilization of 40 gigatons of CO2 per year. You know, and luckily there's about 3 decades of scientific literature of ocean iron fertilization experiments. You know, and these often show that there's, you know, really limited carbon export, and also that there can be downstream consequences. So if you take macronutrients out because you're adding in iron, you deprive downstream ecosystems of that productivity, and so that needs to be discounted from your entire carbon removal. So
yeah,
you know, I guess I would say I'd urge you guys to take a look at that.
We certainly have. Yeah. Do you want to say something about that, Franz?
Yes, we have a very different
sort of view.
a very different
understanding.
input
Yeah.
of iron dust into the ocean. What is the trials which had done until now? They used a liquid iron or so, and in a rather high concentration. But if we look back to the glacial time, during the times with very high dust in the air, then the CO2 levels went down, and also the methane levels in the
atmosphere
ice age went down. Only during the dust events. But all the trials until now had been done with liquid iron and not with aerosol, like nature did. And so I think that's a real, totally different situation to the trials which have been done until now.
Yeah, perhaps I'll say something here as well, that it's if you take an area of ocean, I mean, those numbers are big because we're talking about a very large area of ocean, David. If you take a small, a unit area of ocean, what we're talking about, what we're suggesting and proposing, is to increase the primary productivity of that area to 1/10 of the primary productivity that is found quite naturally in other parts of the ocean. For example, the west coast of South America, particularly Peru and Chile, as the most productive fishing grounds in the world, have a primary production of phytoplankton of 20 grams of carbon per square meter per day. So they seem to be working very well. You have the most productive fishing grounds in the world there, as I say. So we've said, okay, let's, with our fertilization, aim to produce 1/10 of that. And then we've looked at the concentrations of it's mostly oxygen, calcium, and other nutrients. We don't really see a problem. Does that answer your question, David?
Yeah, partially. I think it's really interesting, this idea of adding aerosols, and what Franz said about the difference between liquid iron additions and aerosol iron additions. I would urge you guys to think about these downstream consequences, because when you take nutrients, when you take nitrogen and phosphorus out by adding in iron and allowing for productivity to happen, you deprive a downstream ecosystem of the productivity that would have happened. And so you have to discount that when you're considering carbon dioxide removal on decadal to century timescales.
I understand your urging, and yes, David, we agree that should be looked at, and we have looked at that, and we will continue to look at that. Okay, thank you.
I was just going to say, just in answer to Dave's comment as well, we've just had a massive dust storm blowing off the Sahara over the Atlantic Ocean, and certainly that might give us a good analog to try and answer some of those questions that you are raising at the moment.
Yeah, right now we don't have funding. This has been produced by people from their own resources at home, and in Franz's case, for 20 years. We think that this would be one of the many measurements that should be taken. If there's it begins with a small trial, absolutely, downstream nutrients should be measured. I totally agree with you, David. So I think there's not any argument there. We certainly began with the same concern, and then we realized, well, we don't think it should be a problem, because we're really only doing what nature has done in the past, as Franz just said, in the glacial periods when iron blew over, lots of very fine dust blew over more widespread over the oceans, and it induced a faster drawdown of CO2, which is why it ended up less than 200 parts per million. Thank you. Andrew Lockley, please. You have to go off mute.
Yeah, I was just scrambling from a Zoom app.
Mm.
So I'll put my face on in case anyone wants to see it as well. You can't see very much of it because there's a light behind me. So yeah, I've got a couple of concerns with this. The methane thing, I'm not so sure about. That putting a lot of chlorine radicals into the atmosphere has got a range of possible problems. If they get folded into the stratosphere, as they will tend to if they get lofted into the upper troposphere by thunderstorms, then the chlorine radicals in the stratosphere are generally pretty bad news for the ozone layer. And that's going to require quite detailed modelling to make sure we know the effect of that if we're going to deliberately load the troposphere with a lot of sources of chlorine radicals. Now, obviously, salt itself has chlorine in it, and the huge amount of sea salt ends up in the atmosphere through aerosol lofting. So it's difficult to untangle those effects, and that's going to require detailed computer modelling. But a more fundamental concern I've got is with the iron budget, because the iron budget is the idea of using iron for geoengineering purposes has been reasonably well tested, much more so than most other geoengineering techniques, and frankly widely debunked. There are a couple of fundamental problems with this, and some of them have been discussed on the call, and macronutrient scavenging, but there's also more general issues in that the carbon, fundamentally the carbon exists in one of two states. So it's either labile carbon or it's exported into benthic layers where it remains. Now, if it's labile carbon, then it's moving around and around and around in the ecosystem, and it's a fairly good way of making fish and a really bad way of doing carbon sequestration. Now, if it goes down into benthic layers, then it'll either get recycled and remain labile, so it's deep water labile carbon, or alternatively, if there's enough of it, then you get euxinic conditions in benthic layers, and to describe that as a major disruption to ecosystem is like describing the bomb dropped on Hiroshima as quite a warm day. It just doesn't do it justice. You're looking at a catastrophic change to the global ecosystem if you're exporting non-metabolized carbon at scale into benthic layers. You're looking at the kind of environment that is typical of hothouse Earth conditions, and stationary oceans.
I understand the question, Andrew. I'm just wondering whether to put a slide up. The amount of carbon, perhaps I'll put the slide up. Let's do it.
Well, just to summarise what you're doing, that it either doesn't sequester carbon, or you wouldn't want it to.
Can I say something to that?
Yes, please, Franz. Yeah.
We want to use maximum 250 or 280,000 tons of iron. That's a little bit more, double or 3 times more than naturally falls down of iron into the ocean. So, and soluble iron. That is good reference and has been found. So, to increase the amount by the factor of 3 of the naturally falling down iron into the ocean will not disturb the ecosystems in a catastrophic way, as you say.
Well, if that's the case, then it's not going to sequester much carbon, because what you'll do is you'll introduce labile carbon into the ecosystem, which will form fish and plankton and macroalgae and all of the other joyous things that are in the ocean. But it won't have a lasting increase on export from the surface ocean into benthic layers and into sediments. And if it did, it would be a major problem. So, you know, the idea that that can be touted as a significant benefit in terms of carbon sequestration is not defensible in my view.
Yep, I understand your logic, Andrew. I think we don't agree with your initial premise. Different parts of the ocean are very different. We're talking about applying iron salt aerosol to parts of the ocean which are very iron poor, where nothing much is happening.
I'm aware of that. I'm not disputing that, but what I'm saying is that that alone doesn't do much to export carbon to benthic layers.
Yeah. Okay. So let's.
I've got a top level question there, Clive.
Peter, let's just see if I can deal with this with Andrew, and then let me come back to you, Peter, because I think there's another question as well. So here's what we see the effect on the ocean carbonate system. Let's not go through this stuff here. The amount of dissolved inorganic carbon in the ocean is 38,000 gigatons of bicarbonate and carbonate anions. So if we're talking about putting in 40 gigatons of CO2, that's 10 gigatons of carbon. That's a 0.026% increase in dissolved inorganic carbon per year. I don't see anything catastrophic about that.
But you're not putting that in as dissolved inorganic carbon. You're putting that in as organic carbon because you're using the iron to stimulate the uptake and bioaccumulation of carbon. And if those plankton or whales or whatever it is you form die, the only way they can export from the surface ocean system is to descend to the benthic layers as marine snow, right? That's that's the only option open to them.
They become oxidized until they are fallen down. They will not come to the ground.
Yeah. Well, this is the reason we're working on this very long paper, and it says just what Franz just said. Fish, and it's mostly microbes, organic carbon, it oxidizes within the first mostly 500 meters. This is why you see a drop in pH in every part of the open ocean, where it's oxidized back to bicarbonate, mostly bicarbonate.
Okay, but the iron associated will then return into the surface, into the mixed layer of the ocean during that process. So your iron will cap out fairly soon, or it will.
They go into hydrocarbonate. That's all. That they oxidize.
Yeah,
but
Andrew's saying the iron. Andrew's saying that the iron remains available. So so there would be a build-up of iron in the ocean. So primary productivity continues.
So if you've got a build-up of iron, then one or two things will happen. Either you'll have diminishing returns where the iron is just building up, but it's not making any difference because the ecosystem's no longer iron limited, right? Or alternatively, you'll have a situation where the iron is being actively exported in marine snow, and in which case you're back to the problems that we discussed. But your argument is that as far as I can tell, taking your argument at its highest, you're looking at an increase in ocean biomass in the mixed layer and slightly below. But you're arguing that won't be exported to benthic layers where it would be problematic. So you're basically turning a desert into a forest. Now, if that's the case, then that's it's not trivial, but you'll quickly cap out. You're not going to be removing that amount of carbon for very long because that layer will quickly saturate. You'll become light limited, or you become macronutrient limited, and those productivity gains will cap out. So you might have noticed a relatively swift change, as Ross George's experiments suggested. But after that, there's no further increase to be had unless you start conducting, really serious large-scale changes to benthic ecosystems, which are pretty dangerous.
No, we certainly don't want to do anything that's dangerous. I'll just go back to the answer I gave before. What we're proposing is to take areas of the ocean that are doing very large areas of the ocean that are doing virtually nothing, and give them a productivity, induce in them a small increase in productivity. That over a very wide area adds up to a lot.
Yeah, I understand that, but what's
the
long-term budget?
And we will look during our trials what happens down there, and we will look for the oxygen content and all other parameters as to rule out such catastrophic scenario.
But what's the long-term budget? Are you expecting, in the long term, are you expecting the iron levels to plateau, or are you expecting the iron levels to continue to increase? And if the iron levels are plateauing, then that indicates that there's an export of both iron and accompanying carbon into benthic layers. And that is only going to end up by the,
we have in the ocean a very different kinds of iron concentration, and we would not get higher than normal. For instance, in the Atlantic is a much higher concentration than in the Pacific,
I understand.
Or in the deep sea. You have much higher iron concentration than on the surface.
But what I'm saying, in the long term,
because iron is raining out.
Okay, but in the long term, where is this iron going to end up?
You've gone a bit muffled and quiet.
Sorry. What in the long term, where is this iron going to end up? What's the sink?
We don't think we need this action 50 years long, because this is a rather short thing. What we
yeah. But basically, what we're proposing wouldn't do anything to the ocean that there isn't already some ocean that's like that anyway.
I think, guys, you're missing the point, because let's get back to the whole concept of restoration. And one of the fundamentals that we have is that we have dramatically reduced the biological nutrient cycles across the planet by reducing the overall amount of life. And if you go back into the old fisheries records, it quickly becomes apparent that the total amount of living biomass in vast areas of the oceans has dramatically reduced. And that's the whole function of the biomass. It's the whole trophic triangles that were functioning within it. So you look at the old fisheries logs off Newfoundland and the North Atlantic and what people used to catch, and the amount of weight of fish that is recorded per ton massively reduced. Now, if you've got a lot of biomass functioning in the ocean, all of those nutrients are in continuous circulation. So you get a big dust storm coming off Africa like the one we've had, and that dust lands in the ocean and just sinks through the water column. If you can maintain it over a long period of time so that you build up that life and it lands on a healthy ocean, it'll take those nutrients and keep them in circulation. And then the next one comes through and refreshes it. But without lots of life there, that process won't maintain the nutrients in circulation. So the flaw in all of the studies that have been done on ocean fertilization so far that I'm aware of is that their duration has been very short. You create a plankton bloom, but you don't grow the ecosystem underneath it, and you don't have time to monitor it. As you build up a complete ecosystem, the way the carbon gets transported through it becomes quite different. Vast numbers of zooplankton that are transporting up and down day and night and are defecating when they get down below 1,000 meters are drawing carbon down into the system, and it gets trapped lower in the ocean. So there's a whole host of things we don't know. But what is clear is that if you've got a lot of biomass on the planet, if the whole system is working properly, then it becomes much more robust and it's capable of dealing with further emissions. So one's got to be long-term over this, and one's got to think about nursing ecosystems back into existence. And this is particularly true on land, and it's also very true of the coastal ecosystems as well. But the first part of this objective is to try and draw down atmospheric methane and try and reduce the very intense heating effects we've got when we're looking over Siberia, Lapland, Kara Seas, and those sort of places, where you've got effectively a heat lens. holding temperatures really high at the moment. So yeah, we need research. We need to, I think, to have it focused. One needs to get away from the fear of talking about massive problems it will cause, because we need to be working with small areas consistently over time and get experience of recovering ecosystems and drawing. I think something like the Arctic Sea there, Latvia, Kara, taking one of those seas and working on it to see what you can achieve and get proper measurements and look at what's happening to the biomass in that water. And then they've got a whole series of questions over the summer-winter cycle that's going on and what times we should be working on that. And what other technologies you need to be integrating it with at the same time. I mean, you know, if you're going to take one of those seas, you might work really hard as the winter approaches to stop the ice forming, so you get maximum radiation of heat back out of the oceans. And then come the spring, do everything you can to retain the albedo.
Okay, thank you very much. Yeah, thanks. Very helpful answer. Thank you very much, Brew. I'm just thinking about the time. It's 10:05. I'm happy to continue. If anybody needs to leave now, I said it would be, well, I just said it'd be 30 minutes plus Q&A. Then we can't stop you leaving. Thanks for those questions. Let's have this. Sue Lee has had a hand up for a very long time. Sue, please.
Yeah, so my question is about chlorine radicals and the concentration of chlorine where you are applying ISA. I've heard that folks have expressed concern. They're not sure if it's a safety issue. I've also heard that it's only local and maybe even only at the nanoscale, and also that chlorine could be recycled to reduce the overall concentration of chlorine. Can you comment on those?
Yes.
Okay,
if you have the plume, the chlorine doesn't disappear from this plume. You got the aerosol plume, you know. It will not disappear. It recycles always, you know. And the chemistry, what Clive told before in this picture, is a rather complicated, because the chemicals of the atmosphere, there is, for instance, H2 hydroperoxide.
Hydrogen peroxide.
In the atmosphere, additional to these chlorine atoms. Also, OH atoms are produced. So we will test the mechanism and look what happens in nature outside.
Mm-hmm.
Because we until now we have some trials in climate chambers. There are 3 or 4 papers made from climate chambers tests in the University of Bayreuth.
Yeah.
And we hope to go on in Copenhagen in another climate chamber to get more results before we go into the field.
So yeah, I think your question related to safety, Susan. Is that right?
Yeah. So when we talk about ISA, we hear concerns about safety and want to know whether it's something that can be easily put to rest by explaining that this is local. I think someone earlier raised the issue that it's only applied where the ocean is there's not much going on in these remote areas, these local areas of the ocean. So does that mean we can just respond and say, look, it's not going to be a big hazard to a huge ecosystem?
Yeah, we don't think it would be a hazard to any ecosystem because the concentrations are still very low. Is that right, Franz? The concentrations are still so low that nothing is going to be affected. Birds will fly through it; they won't even notice.
You have one slide with the milligrams per square meter of iron.
Yeah.
Per day.
Yeah.
It's extremely low. I think in a town with next to a street, you have more iron and dust.
Iron aerosol dust blowing about.
What we're looking for the methane effects, Susan, is that recycling that you referred to via photocatalytic action, and that goes on already. And there's a good paper. I'll send you a link. Where there was there's I think there's a factory in China has a fair amount of iron in its chimney, which is acting in the catalytic effect that we're looking for. So the kind of things that we are looking at, the kind of chemical processes that we want to enhance, and natural processes that are already happening in the atmosphere. And it happens when you put your washing out. If you put damp washing out on the line, you bring it in once it's dried, it smells, and you have that lovely fresh sort of odor in your washing. And Matt Johnson, who's working with us in Copenhagen, was the author of the paper looking at that effect that gave washing on the line that nice clean odor.
Smell.
And it's basically that, what's happening in the damp washing is the same process that we're looking at. It's replicating in the atmosphere, and so we've already got particles in the atmosphere doing what we're looking for. What we're trying to do is increase them by a relatively small amount and capitalize on the photocatalytic effect. So coming back to what Franz is saying and what Clive alluded to before, the concentrations that we need are minuscule, and so we should inherently be safe. The other thing that Andrew raised as well was, what's the risk of the chlorine atoms being wafted up into the atmosphere? Well, generally, one of the things that we have with iron salt aerosols is that they get washed out the atmosphere very easily. So it's not like HCF gases and CCFs that did not get washed out the atmosphere and rose naturally up into the stratosphere. So we don't envisage that this will rise significantly up into the atmosphere, though it's obviously something for us to look carefully at. But I think we're not talking about something that is on anywhere near the same kind of magnitude of risk that we've had in the past with other unwanted gases going up into the stratosphere. So great. I think your points are right, and we're gonna have to really make sure that we've got those well and truly established. Hopefully, when we get the computer modeling, we should get a better idea of that. But the initial perception at the moment is, safety-wise, it's not a big issue at this stage, and it's a sufficiently low risk at this stage for us to start betting on it. Right. As opposed to something like CCF, which just went straight up and ripped the atmosphere to pieces. I think as Franz said, as Clive said as well, this may actually have some ozone protective effects. So, for example, if we can release ISA in low levels, then we can deplete ozone at the troposphere, and we also deplete other ozone depleting gases from the troposphere as well. It has an effect on HCFs and CCFs.
And so halogen, yes. Halogen.
Yeah, so it can potentially stop those gases going up into the stratosphere. So what we actually hope to see is it has a stratospheric positive effect. The other thing on the stratosphere as well that's extremely alarming just now is the rise of methane in the atmosphere. So methane is slightly lighter than air, and it's now being released at a sufficiently fast rate so that large quantities of methane are now already ending up in the stratosphere. So there really becomes an increasing onus for us to try and find a way of intercepting the methane as it transitions from release at its ground level up into the stratosphere.
Because once it gets in the stratosphere, it's not depleting and
Exactly.
to
Yeah. Once it's in the stratosphere, its half-life is something like 200 years. So it's bad enough in the troposphere. When it gets into the stratosphere, it is 20, 30 times worse. So the global warming potential of methane, I would suspect, is going to increase significantly as the concentration increases. It's the ultimate mechanism for creating a totally unstable feedback loop on top of all the other feedback loops, which will then interact with as well. So it really is an incredibly delicate situation that we are in at the moment.
And the warmer it becomes here below in the troposphere, the colder the stratosphere becomes, and it makes these stratospheric clouds which destroy ozone.
It's another feedback
essentially
mechanism. Another feedback mechanism.
I'd like to just correct something, Kevin. The total amount of air above this, in the stratosphere and above, is about 6% of the atmosphere, as I recall. And so the concentration of methane is going to be fairly similar in the stratosphere and the troposphere. Obviously, it's removed in the troposphere. That there's no way for the stratosphere to have higher concentration because it'll diffuse back down into the troposphere. My point is that when I've done the calculations, there's not going to be a significant, maybe 2% more warming from increased methane in the stratosphere, which is really, I don't think, significant.
Yeah, it's good point, Peter. The fact, though, remains that we are getting methane getting into the stratosphere. The methane then has a number of impacts in that area. It depletes methane, it depletes ozone. It starts creating high-level clouds as well. So it's not just the methane that is causing the warming when it gets into the stratosphere. It's all the other knock-on effects. And again, coming back to what Brew was just saying, it is the longevity of methane when it gets into the stratosphere. Bear in mind, in the past, it never used to get there. It does now.
And of course, it keeps building up because it's not going away anymore. So
yeah,
it's not like the methane that we talk about because it gets depleted.
Yeah. It is a different set of equations that are now coming into play, and everything is cumulative.
But the bottom line is reduce the. Let's do the ISA and reduce methane levels in the troposphere, and then we can stop the discussion.
Yeah. Great. Yeah. Just to say one more little thing about Susan's question. Can you see this? I'm slightly concerned that people will look at this diagram and they will see a very high concentration of characters talking about chemicals. This all looks like a huge concentration of chemicals, but these characters have to be big so that we can read them. It doesn't mean that it's a representation of the concentration. Does that make sense, Susan?
It does, and I think messaging and how you communicate it to the general public is going to be very important, because people will, have knee-jerk reactions. So, I mean, I think one thing that we do is, we try to do messaging targeted for specific audiences, and we'll keep that in mind to make sure that we talk about it as something that nature is already doing and something that we already see happening when you dry your laundry, or things that we are already doing, and we don't see a catastrophe in the ecosystem.
Yeah, very good. Thank you very much. Okay.
And Yeah, I say that segues to my question of
yeah.
Who's the audience? So in the chat I had said, why do you think there's no funding? If there were funding, who would fund it, and why would they fund it?
Anyone like to answer that?
I think there's no funding for a number of reasons, Peter. I think, as we all know on this call, that there has been a big pushback for years from various NGOs and governments against any form of research on geoengineering, not just having geoengineering, but even having any research in it. So there is that momentum that we have to push back and fight against, and there's still no clear position that's been advocated on this from the IPCC. So we've got that as an issue. The other issue is there's really not much of an easy way to commercialize this yet. So when you look at things like the only carbon trading mechanism of major note at the moment is the EU ETS. And that doesn't cover methane, nor does it cover radiative forcing. So there is no market mechanism at this stage. And it's very much it's a horse and a cart kind of thing, or a chicken and egg, or whichever one whichever analogy that you want to use. I mean, somehow we need to prove this, and then once it's proven and demonstrated to be safe, and it meets the concerns that people are raising here, then we can have a dialogue and a conversation with government. But then governments say, well, you're not going to get any funding or any political support until you can demonstrate safety. And so we are trapped in the horns of this dilemma all the time. I've always been a believer that maybe one source of funding one day might come from the insurance industries, who would surely, it must be in their interest to be able to address climate change. And I have spoken to insurance organizations, and even they're not interested. It is incredibly difficult.
So are we trying to solve a problem that's not a problem? That is, I grew up in a family of economists. I was the only one who didn't get an economics degree somehow. But they would say, listen, if you don't have any buyers, you've got a product that nobody wants. Do we have a product that nobody wants?
Everybody wants to stay alive on this planet.
Can you prove that?
We just don't know. The key
what's the evidence for that?
Introduce people to the idea that they need the product. Once you tell them they need it, then they understand it, then they'll buy it. But
so it's a marketing. So if it were a marketing issue, who would the buyer be? Who would we be marketing to?
Well, what we need to be doing is we need to get intergovernmental policy transformed to have this now as the number one target. The number one target has to be thinking how we intervene in the climate system. That's where we need to be going.
Any final comments from anybody at all before we say goodbye? We do actually have a young man, Felix Taubert, in Germany.
Yeah.
So you're from a business school of chemistry, and you've been sent along to learn about iron salt aerosol to do a research project on. Is that right?
Yeah, I will write my bachelor thesis about the topic methane emissions from permafrost.
Yeah.
And the reduction from methane with photocatalysis and iron salt aerosol method.
Oh, brilliant.
Yeah. Well, would you be willing to share your thesis with us?
Yeah. That's fantastic. So is your work ready to publish?
No.
You are in the state of how do you say it? A bachelor. You make a bachelor work, and yes. I hope you will go on working on the university and make your master and so on the same theme.
Yeah, I mean, it's a really interesting topic. And yeah, how you said, Mr. Elsworth.
Yeah. Okay, excuse.
No, I mean, the methane is a big problem, and global warming, global GWP, global warming.
Yeah. Potential.
global warming potential, and it's a topic for the future. So I mean, ISAs are a really helpful method to
Being the right thing.
yeah.
Well done. No, keep it.
Yeah. Great. Thank you very much. Thank you, everybody. And anybody who wants to stay in touch, you've got my email address. If you'd like to be included in these in the future, let me know. Thanks, everyone.
And if Felix has any question, he can ask me directly.
Okay, thank you, Mr. Este. Thank you.
Okay.
Okay, guys. Thank you all.
Thanks for sitting up, Clive.
Good job, Peter.
Sure.
Thank you.
Yep.
Thank you, everyone.
Sure.
Cheerio.
Goodbye.
Bye-bye.
Good to see you.
Bye. Thank you.
Bye all.
Bye-bye.
Hi, Doug.